Hello everyone, welcome to CE 3 to 11 Principles of Steel Design. So in this series of videos, we would be discussing about the analysis and design of tension members. Okay, so when you are to design a certain structural member, the first thing that you should take into consideration is the manner in which a certain structural member will fail. And after taking note the manner of failure, you must then design that certain structural member to resist the failure that you have anticipated. So for pretend that we would be having a certain structural member, and let's say that that certain structural member is to be a compression member. So let's say that this is to be your compression member. So it means that it is subjected with compressive loads. So let's say that this is to be your compressive load P. So P. So like what I have said earlier, that when you are to design a certain structural member, you must first anticipate the manner in which it would fail. And if you are to deal with compression members, the most common failure of it would be failure by buckling. So by failure by buckling, its collapse mechanism, or I mean its failure mechanism, would typically look like this. So it would buckle in this manner. So after knowing the manner of failure, you must then design this structural member right here to resist this kind of failure right here. And that is structural designing in a nutshell. So let's delete this one first, since we are to talk about the analysis and design of tension members. So let's say that we would be having a certain structural member right here, which is a tension member. So let's say that this is to be your tension member. And if we are to talk about tension members, so it means that it would be having tensile forces. So let's say that this is to be your tensile load P. So this is to be P, and this is to be P. Okay, so in tension members, the most common failure are the following. So the first limit state, or the first failure that I would be showing you, is what we would be calling cross-sectional yielding. So for your cross-sectional yielding, so yielding in steel design is actually your excessive elongation. This failure right here would only occur if your force P is high enough for you to reach your yield point, or your yield stress, or your Fy. So for us to know the limit, so let's say the nominal force Pn, so let's say that this is to be Pn. So Pn is actually equal to your yield stress. So your yield stress is equal to Fy. And if you would be multiplying it by the cross-sectional area Ag. So once again, your Pn is equal to Fy Ag. So this Pn right here is actually the limit, or your force P, the force P required for your tension member to yield. So once again, if this force Pn right here is to be applied here, so let's say that this is to be force Pn, it means that this certain structural member right here is actually yielding already. Okay, so of course we don't want that to happen. So that's why in steel design, AISC has accepted two major design methods. And those methods are as follows. So the first design method that is recognized by AISC and NSCP, they are to be called ASD. They are to be called LRFD and ASD. So ASD. So this is to be two of the major design methods that are recognized in steel design. So in LRFD, this is your load resistance factor design, and in ASD, this is to be the allowable stress design, or the allowable strength design. Okay, so in LRFD, so considering this equation right here, we would be adding a reduction factor. So in LRFD, this is to be your design strength, PU. And in ASD, your allowable strength is PA. So once again, in LRFD, design strength, and in ASD, allowable strength. So your PU is equal to phi Pn, whereas this value of phi right here is to be your reduction factor. And for PA, So for your allowable strength, if you are to use ASD design method, that is to be Pn divided by your factor of safety, omega. So factor of safety. And if we are to talk about cross-sectional yielding, the values of phi and their omega would be as follows. So you better memorize these values right here. So phi is equal to 0.9. So since this is a reduction factor, this value should be less than or equal to 1 since we are reducing this strength right here. And for PA, or for our omega, for ASD, our omega is equal to 1.67. So from that, if you want to determine the value for PU, so P's of U is equal to phi PN. So phi PN, and the value for our PN is equal to FYAG. So phi FYAG. And for ASD, that is to be, so PA is equal to PN over omega, and our PN is equal to FY times AG. So FY times AG divided by omega. So there. So once again, if you are only to talk about yielding or cross-sectional yielding, this would be your reduction factor and your safety factor respectively. So by the way guys, if you are to consider analysis and design, so the main difference between these two methods right here is when you are analyzing a certain structural member, you are actually solving for the maximum load that it can carry. So in analysis, you actually have your member already. So if you already have your member, you have your value for your AG. So AG, and using your value for your AG or the parameters involved, you must solve for either PU or your PA. So that is for your analysis. So considering this one right here, the parameter of this certain section right here is already given, and you are solving for the maximum allowable force P. So that is for the analysis. And as for the design, it would be the other way around, whereas you have your value for PU or PA, and using these values right here, you would be arriving at a certain AG or whatever parameter that you would be solving. So what that means is that in the design of tension members, you have your load P, and you would be choosing for a member that can carry that load P right there. So that is the difference of analysis and design in structural engineering. Okay, so going back to the task at hand. So once again, this would be the first failure that I will be showing you when we are to talk about tension members, so cross-sectional yielding. So another thing that we should take into consideration is what we would be calling tensile rupture stress. So once again, this cross-sectional yielding right here is your excessive elongation, and for your tensile rupture stress, we are to assume that your member is ruptured, or ductile fracture as we call it. So instead of elongating, it is already broken. So there. And the value for your phi, for the value for your PN here, so your nominal P, so let's say that this is in this certain connection right here, this is to be your load P, this is to be your load P, P and P. And for your nominal P, for this section right here to experience rupture, that is to be equal to FU times AE, where FU is equal to your design, where FU is equal to your ultimate stress, or the ultimate stress of your section, and AE is to be the effective area. So we wouldn't be using our cross-sectional area here. Instead, we would be making use of your effective area. So as for FU, this is given, or this can be seen in the tables that I will be showing you later. And as for AE, so note, your effective area is equal to your shear lag factor times the net area. So there. And for your shear lag factor, you can see this. I mean, you can see the value for your shear lag factor using the table that I will be showing you later. And as for area net, which is AN, that is basically the cross-sectional area minus the area of the hole. So let's abbreviate it as A holes. Okay, so why is this the case? So in cross-sectional yielding right here, the location of the failure would be in this location right here. So if you can see the yellow line here, so it would be this one right here. So this one would be the one that would experience yielding. That's why we would only be using cross-sectional area. And as for our tensile rupture stress, so the failure plane would be in this location right here, wherein we already have our holes. So by the way, guys, these blue circles right here indicates that these are the bolted connections. So this is to be your gusset plate and this is to be your member, and they are connected to each other. And once again, tensile rupture stress would occur in this part right here. So there, and from that, since this is to be the whole area, so this line right here is the representative of the cross-sectional area, and the area of the holes will be this one right here. So we would be subtracting these parts right here. So this blue, that blue line right there that I have highlighted green. So rewriting this one right here, that is to be the cross-sectional area minus the diameter of the holes. So let's say the diameter of the holes times the number of holes, so n holes, times the thickness of the plate, so times thickness of the plate. So this is to be your area net. So this is to be your area net, which you can substitute in this equation right here, and after that you can solve for AE and you can substitute it here. So that is for the formula for tensile rupture stress. So there, and similarly with the previous slide, we will also consider LRFD and ASD here. PU, or the design strength, is equal to phi PN, and for ASD, your PA, or the allowable strength, is equal to PN over omega. So there, but the major difference here between the tensile rupture stress and the cross-sectional yielding is that your phi here, your phi in tensile rupture stress is equal to 0.75, and your omega in your ASD is equal to 2.00. So this would be the reduction factor and the safety factors that you would be using in these equations right here. So if you can see here in this slide right here, our phi and our omega in cross-sectional yielding is 0.9 and 1.67 respectively. And in tensile rupture stress, that is to be 0.75 and 2.00 respectively. So the third common failure for tensile members is what we would be calling block shear. So block shear. So we already have our spoiler here. So this is to be the equation that we would be using. So what is block shear? So suppose that this is to be your structural member. So instead of this one right here yielding at this point, so just like a while ago, if it yields in this point right here, this is what you would be calling cross-sectional yielding. And if it would rupture in this point right here, this is to be tensile rupture stress. And for your block shear, so let's say that this is to be your connection, it can fail in this point right here. So this is what you would be calling block shear. So let's say that this is to be the manner of failure. So we actually have two possibilities here. So this part of your plate right here can be disconnected from this part right here, or it can also fail in this manner right here. So instead of the one that I have shown to you a while ago, it can also fill in this manner, whereas this part of the shaded area right here be disconnected from this part right here. So if you are not sure whether this is to be the failure or the other way around, or let's say the one that I have showed to you a while ago, which is this one right here, it is better for you to solve for it, and whichever the case that would give you a much lesser value, that is to be the governing one. So this is to be the formula that we would be using. Oh, by the way, this is to be the manner in which it would fail. So in reference to bgstructuralengineering.com, so this is, these are two of plenty of ways a certain structural member would fail through block shear. So let's say that we would be having this, and this is to be your tensile loads. It can fail in this manner, whereas this part right here was disconnected from this part right here. So there, and as you can see here, this part right here, or this certain area right here, is actually perpendicular to your line of action. So meaning this area right here is to be your tension area. So that is from your mechanics of deformable bodies or your strength of material subject. And if your area is parallel to your line of action or your force, that area is what you would be calling your shear area. So we have your tension area and your shear area. So it would be similar to this one right here. So we would be using these areas right here in solving for your block shear, which is well indicated in this formula right here. There in this formula right here, this is to be 0.6 FU ANV plus UBS FU ANT, and it should be less than or equal to 0.6 FYAGV plus UBS times FU times ANT. So for this FU right here, this is to be your ultimate stress. And as for this ANV right here, so ANV is to be your net shear area. So that is for ANV. And for your ANT, this is to be for your net tensile area, net tension area. And as for this AGV right here, this is to be for your gross. And there. And another new parameter here, or another new value here, is this value right here, which is UBS. And this is to be your block shear coefficient. So this is pretty much basic. You would just be using these figures right here by AISC. So if your connection is either of this following or similar to these ones right here, your UBS is equal to 1.0. But if your structural member is in this connection, in this setup right here, your UBS is equal to 0.5. So there. And since block shear is a rupture limit state, you would be using 0.75 for your phi, for your LRFD, and for your ASD, you would be using an omega of 2.00. So it would be very similar to your tensile rupture stress. Okay, so that is to be the three major failures that we would be considering in the design and the analysis of tension members. So let's have a summary. Okay, so let's have a summary here. So for tensile members, this would be the most common failures that you should anticipate. So once again, the first one is to be your cross-sectional yielding, which we would abbreviate as GSY. And for the second one, so let's say that this is to be your tensile rupture stress, which is TRS. And for your block shear, let's say that it would be this one right here. So it's B. S. So for GSY, our PN here is equal to FYAG. And for our tensile rupture stress, our PU here, our PN here is to be equal to FU times effective area. And for our block shear, since it is very long, I would just paste it here. So this is to be the formula for your block shear. So for ASD, so let's say that this is to be for ASD, and this is to be for LRFD. So once again, for your ASD, this is to be PA is equal to Pn over omega. And for your LRFD, so I would just be writing it here since you don't have any space. Rather, I would just be moving it here. So there. So for your LRFD, Pu is equal to phi Pn. So for the values of your omega, so for cross-sectional yielding, this is to be 1.67. For tensile rupture stress, that is to be 2.00. For block shear, that is also 2.00. And for LRFD, for the values for your reduction factor phi, so that is to be 0.9, 0.75, and 0.75 respectively. So there. Okay, so this would be our reference for this lesson. So we would be using the National Structural Code of the Philippines 2015, 7th edition. And another reference for this video lecture is the book by Jack McCormack and Stephen Cernak, which is Structural Steel Design, 5th edition. Okay, so using these books right here, so using this structural design book by McCormack and Cernak, we would be using these tables right here. So this is to be for the workable gauges for your angle. So this is to be page 71 of this book. And for your nominal hole dimensions, that is to be page 401 of this book right here. And if I'm not mistaken, this is also in the book by Astm, which is the National Structural Code of the Philippines. So another table that we would be using here is this one right here. So this table right here is for your shear lag factors for connection to tension members. So this is, if you can remember our formula earlier, so for tensile rupture stress, that is to be Pn is equal to FUAE, and our AE here is equal to AN times U. So this would be the values of your U depending on the case here. So it is better for you to read all of the cases, then apply whichever case is applicable to the structural member that you are designing or analyzing. So this is to be page 5-54 of NSCP 2015. Okay, and another thing, this is to be your Astm specification for various structural shapes. So you can just download this one on the internet. So this is to be a free table. So what this is, what this indicates is the yield stress and the ultimate tensile stress of your steel. So whichever Astm designation it might have. So for pretend that you would be using A992 steel. So if you are to use A992 steel, meaning that your Fy or your yield stress would be 50 kips per square inch or 50 ksi, and your tensile stress would be 65 ksi or 65 kips per square inch. And another thing, so we would be using this AISC shapes database, which is a free Excel file from AISC. So you can just download it there, or you can just download it in the description below. So if you would be having your AISC shapes book, or let's say that you have your strength of materials book by Ferdinand Singer, you can use those to get the parameters of your shapes. But if not, you can just download this free Excel file.